We're going to look at graphs of functions of the form ax to the n, graphs of general polynomial functions, behavior at zeros, turning points and end behavior, graphing techniques, the intermediate value and boundness theorems, approximations of real zeros, and some polynomial models. As with quadratic functions, the absolute value of a in f of x equals ax to the n determines the width of the graph. When the absolute value of a is greater than 1, the graph is stretched vertically, making it narrower. When the absolute value of a is between 0 and 1, then the graph is shrunk or compressed vertically, making it wider. Compared with the graph of f of x equals ax to the n, the following holds true. The graph of f of x equals negative ax to the n is reflected across the x-axis because of the negative in the front. The graph of f of x equals ax to the n plus ak is translated or shifted up k units if k is positive, and the absolute value of k units down if k is less than 0. The graph of f of x equals a times the quantity x minus h to the n is translated h units to the right if h is positive, and it will translate h units to the left if h is negative. The graph of f of x equals a times the quantity x minus h to the n plus k shows a combinations of these translations. Depending on h, it shifts left or right, and depending on k, it shifts up or down. Example 1. I want to graph each polynomial function. Determine the largest open interval for which the domain is increasing or decreasing. If you look at this graph, we notice that there's an x to the fifth minus 2. So I'm going to graph x to the fifth first, and then we'll shift it down 2 because of this negative. So let's make a table. I'll have x, y, and we'll pick some values. Let's say negative 2, negative 1, 0, 1, and 2. Negative 2 to the fifth power is negative 32. Negative 1 to the fifth is negative 1. 0 to the fifth is 0. 1 to the fifth is 1. And 2 to the fifth is 32. So this is the graph of x to the fifth. But I want to graph x to the fifth minus 2. So this is going to affect the y coordinate. It's going to cause all of the y coordinates to be subtracted by 2. So that's what I'm going to do. I'm going to make another table. The first coordinates are unaffected, so we'll just copy them down as is. But the second coordinate will be subtracted by 2 each. So this is negative 34, negative 3, negative 2, 1, and 30. Now we can plot these points on some graph paper, and we'll be able to graph these functions. And here's the graph of f of x equals x to the fifth minus 2. And as expected, it's shifted down 2 units from x to the fifth. Now if you want to graph these on a computer, you can go to desmos.com. It's a good resource to graph these expressions. The graph will be the same as the function f of x equals x to the fifth, but it's translated 2 units down. This function is increasing on its entire domain from negative infinity to infinity. Part B, we want to graph f of x equals x plus 1 to the 6th power. Notice that the 1 is on the inside, so that means it's going to shift our graph left 1 unit. I know it's going to shift us left 1 unit because this is in the form x minus h. So since this is a positive 1, there's really a double negative inside it. And I know this means we're going to shift our graph left 1. So let's make a table, and I want to graph x to the sixth, and then we'll shift it to the left one. So we'll just pick some points again. Let's say -2, -1, 0, 1, and 2. -2 raised to the 6th power is actually positive 64. -1 raised to the 6th is positive 1. And 0 to the 6th is 0. 1 to the 6th is 1. And 2 to the 6th is positive 64. So this is the graph of x to the 6th. But remember, I want to shift it to the left one. So for each of these x coordinates, I'm going to subtract 1 from it. So we have -3, -2, -1, 0, and 1. So all of the x values are shifted left 1. We do subtraction of 1 to show that here. And the y coordinates, they stay the same. They're not affected. So now we can plot this on graph paper so we can know what this looks like. And here's our graph. It looks like x to the 6th, and it is shifted to the left 1 unit here. You can tell by the vertex here at the bottom. In f of x equals x plus 1 raised to the 6th, the function f of x has a graph like this of f of x equals x to the 6th, but since x plus 1 is inside, and that gives us a double negative, it is translated 1 unit to the left. This function is decreasing from -infinity to -1, and it is increasing from 1 to infinity. For part C, I want to graph f of x equals -2 times the quantity x minus 1 cubed plus 3. Notice that this 3 on the outside is going to cause our graph to move up 3. And the -1 on the inside causes our graph to move to the right 1. And this negative in the front causes a reflection. This 2 here is going to cause our graph to stretch. For this problem, I'm going to build a table, and this is a good technique when you're graphing things by plotting points. The textbook does it slightly different, but you can use either method that you like. I'm going to start by plotting -2, -1, 0, 1, and 2, and this is the x values. Now I want to create this function at the very end, and then I can plot the points for it. So let's start with the inside and work our way out. I'll start with x minus 1. If I plug a -2 into here, we get -3. -1 minus 1 is -2. 0 minus 1 is -1. 1 minus 1 is 0. And 2 minus 1 is 1. So this is now x minus 1. But I want to graph. So in the next column, we're going to have x minus 1 cubed, and we're going to cube it. So I'm going to cube all of these values. -3 cubed is -27. -2 cubed is -8. -1 cubed is -1. 0 cubed is 0. And 1 cubed is 1. So we're getting really close. We have x minus 1 cubed, but we need to multiply it by -2 down in the front. So we'll have another column, -2 times x minus 1 cubed. And I already did the x minus 1 cubed part. So all we need to do is multiply these values by -2. So we get positive 54, positive 16, -2 times -1 is positive 2, 0, and -2. Now you can pick more points than this, so it'll give you a general idea of how to construct this graph. And for the last column, all we have to do is add the 3 on the right side. So each one of these values, we can add a 3. So 54 plus 3 is 57. 16 plus 3 is 19. 2 plus 3 is 5. 0 plus 3 is 3. And -2 plus 3 is 1. And we'll be able to graph our function. And here is our function, negative 2 times the quantity x minus 1 cubed plus 3. The negative sign in negative 2 causes the graph of the function to be reflected across the x-axis when compared to the graph of f of x equals x cubed. Because the absolute value of negative 2 is greater than 1, the graph is stretched vertically when compared to the graph of f of x equals x cubed. It is also translated 1 unit to the right and 3 units up. This function is decreasing on its entire domain from negative infinity to infinity. Notice it falls as you go to the right, so it's decreasing forever. Let's look at some examples of odd degree functions. Here we have the function 2x cubed plus 8x squared plus 2x minus 12 and the factored form for it underneath. Notice that the degree is 3 and we have the tail starts on the bottom left. As you go to the right, the tail ends up on the top. Now if you look at the factored form for it, we have the zeros are 1, negative 2, and 3. This corresponds to the zeros negative 2, negative 3, and 1 on the graph. Now, as soon as we put a negative in front of our odd function, it flips around. We have that the tail on the left is up and the tail on the right is down now. And if you notice the factored form for it, we only have one real zero at 2. The other zeros are imaginary, so we don't have any other roots. For this function, it is odd again. We have x to the 5th plus 4x to the 4th plus x cubed minus 10x squared minus 4x plus 8. And since this is odd, the tail is on the left bottom and the tail is on the right top. Now the zeros are 1 and negative 2, and here we do have the zeros are 1 and negative 2. Now let's look at functions of even degree. If you notice for functions of even degree, x to the 4th minus 5x squared plus 4, the tails are both on the top if the function is even. And the zeros are 1, negative 1, 2, and negative 2, and that corresponds to the x-intercepts. There's 4 zeros here. If there is a negative in the front of an even function, it causes the tails to be flipped. Now they're both in the downward direction. And of course, the zeros are negative 2, negative 1, and 1, and that's where they touch the graph. The behavior of a graph at a 0 depends on the multiplicity of the 0 as determined by the exponent on the corresponding factor. The graph will cross the x-axis at the point c, 0 if c is a 0 of multiplicity 1. The graph has to cross the x-axis if the multiplicity is 1. The graph is tangent to the x-axis at the point c, 0 if the 0 is an even multiplicity. The graph bounces off or turns at the point c. If we have an even multiplicity, the graph is going to bounce off and turn at the point c. So we have two possible scenarios. It could bounce from the top or it could bounce from the bottom. If the graph crosses and is tangent to the x-axis at the point c, 0, if c is a 0 of an odd multiplicity greater than 1, the graph wiggles at c. So we have an inflection point or a wiggle at the point c if the multiplicity is greater than 1. A polynomial function of degree n has at most n minus 1 turning points, with at least one turning point between each pair of successive zeros. The end behavior of a polynomial graph is determined by the dominating term, that is the term of greatest degree, a polynomial of the form f of x equals a sub n x to the n, plus a sub n minus 1 x to the n minus 1 plus all the way to the last coefficient has the same n behavior as f of x equals a sub n x to the n. So all that really matters is the power. If it's odd or even, that will tell us the n behavior. For example, f of x equals 2x cubed plus 8x squared plus 2x minus 12 has the same n behavior as f of x equals 2x cubed. It is large and positive for large positive values of x, and large and negative for negative values of x with large absolute value. That is, it rises to the right and falls to the left. So since this is odd, we know that somewhere on the left it goes down, and I don't know what the middle looks like, but I do know at the right of it, it goes up. The figure shows that as x increases without bound, y does also. As x approaches infinity, y approaches infinity. As we go to the right, 2x cubed gets super large, so the rest of the terms really don't matter as we go to the right. It's going to go to infinity. Similarly, if we go to the left side, as x approaches negative infinity, the y value decreases rapidly to negative infinity because the power is so large. The rest of the terms do not affect the n behavior. The graph in this figure has the same n behavior as f of x equals negative x cubed. Here we have an odd function, but there's a negative in the front. As x approaches infinity, the graph falls as it goes to the right and goes down to negative infinity. As x approaches negative infinity, we're approaching infinity as we go to the left, so it has a rise to the left and a fall to the right. Suppose that ax to the n is the dominating term of a polynomial function f of odd degree. If a is greater than 0 as x approaches infinity, f of x also approaches infinity, and as x approaches negative infinity, f of x also approaches negative infinity. Therefore, the end behavior of the graph is of the type shown here. If we have an odd function, it goes down to the left, and it goes up when we go to the right. Suppose that ax to the n is the dominating term of a polynomial function f of odd degree. If a is less than 0, then x approaches infinity, f of x approaches negative infinity, and as x approaches negative infinity, f of x approaches infinity. Therefore, the end behavior of the graph is the type shown here. So we have a flip. The left side goes up and the right side goes down when there's a negative in front of the x term. Suppose that ax to the n is the dominating term of the polynomial function f of even degree this time. If a is positive, then as x approaches infinity from either side, we have both of the tails go up. If there is a negative in the front this time, if there's a negative in the front, then the tails go down if we go to the left or we go to the right. So the negative in front causes our even function to flip upside down.